class. We took an extra 5 minutes, but that's okay. We'll see that was the first things first, forevers, endeavors. I say the intercepts of f prime needed to match the HLTs. Why do I keep on saying HLTs? What do I mean by that? What am I saying when I say HLTs? Horizontal. Oh, line test. I guess I could just be saying horizontal lines. Horizontal tangent lines? Oh, HTLs. Oh my goodness, I'm doing the wrong acronym. We should sue. I was supposed to say HTLs instead of HLTs. You can tell I teach pre-cal, huh? So ignore all the HLTs and think about HTLs instead. Horizontal tangent lines. Okay. So where was there a horizontal tangent line in this one? I saw a horizontal tangent here, right? I saw a horizontal tangent here, and I saw a horizontal tangent here. What has to be true about the derivative at a horizontal line? So first of all, if you check out this one, the green horizontal line, the derivative needs to have an x-intercept. So the x-intercept of a derivative, hey, like this one, green has an HTL, which means his derivative would need to be crossing the axis right there. So I just think about, like, well, green and orange, green is an original, orange is a derivative, but I don't know if that's f prime and f double prime, or if that's f and f prime, so I have to keep looking. If I look at the purple, purple has a horizontal line at the orange. Uh-oh, that's dicey. So purple could be an original for orange being the derivative. Well, that's sticky because now I just have both of these matching with orange as the derivative. So who comes first? I have orange. I have, oh, this is it. Right here, guys. This tells you everything you need to know. Check out here, right? Don't both functions have intercepts? The green and the purple have intercepts, right? But check it out. Here's how you can know all of their relationships. An HTL only says it has to cross the axis, but question, how do I know, without a shadow of a doubt, by looking at the decreasing before and the increasing after, how do I know that green has to be the derivative of orange, and then purple, ooh, green is the derivative of orange. Well, let's start there. How do I know that green for sure is the derivative of orange? What's the difference? They both have the zeros. What's the difference with the green and the purple? That all I had to do was look at this and I knew it had to be green. Yes, decreasing in a function means negative before, which means I have to be below before, and then above after. Purple was above and then below. Above then below makes a relative maximum. I had a relative minimum. Decreasing means the slopes were negatives or below. Increasing, the slopes were positive. That was probably the other huge technique besides horizontal tangent lines being intercepts. And I had to use that one a lot. I had to use that in Mo's, I had to use that in Danielle's, I had to use that in, who's the other one, Josh Jones? But here, I know for sure green has to be the derivative of orange, and then what we already noticed was that purple could be derived by orange, but orange could not be derived by purple. Actually, orange could be derived. No, orange is derived by green. We already figured that out. So purple must be F, orange must be F prime, and then green must be F double prime. If purple has a derivative of orange, and orange has a derivative of green, then there we go. Was there anybody else's besides Hezzy's? Then let me go ahead and go to Mo's, which was interesting. Oh, this one actually I didn't use the decreasing to increasing because it was below and above for both, but this one was trickier in the sense of approximating the slopes. Let me show you what I meant. I said it out loud, but most of you guys weren't listening. I go to this little curvature line, and I think of, can I approximate this slope? And if I approximate this slope, which seems to be approximately -1, so I could say m is equal to -1. I say, does one of the functions have a value at -1? Well, that one has a value at like -0.5 or something like that, but not quite down 1/1. This is like negative, this would be a lot flatter, it seems like. Unless maybe I approximated wrong, but that doesn't quite seem to work as far as the green being the first derivative. So what if I was to look at the other guy? I should say the green being the original. If I go to his turning point, which, oh, it's right here, bummer. I think I had it right about here. And down 1/1. And I say, well, his slope right there is about -1. And if I go down, -1 is about where the derivative is. So I see like, hey, this -1 seems to mimic the rise over run of the purple. And that's how I knew purple was the original function, because then orange, that -1 seemed to match with where he was, whereas the green was much steeper, so it should have been much lower down. It would have been a much tighter curve. And then there was one other one. You could have kind of done any of these guys. I think Josh Jones, you could talk about it with like a horizontal, or no, vertical shift, and the derivative of any constant is 0. I think that would have been enough for that one. But Danielle's was tricky because all of them, you had even, odd, even again. No, that one you could still approximate with slopes. Which one was I looking at? Maybe Rocco's? Flat, flat, no. Looking for an odd, even, odd. Does anybody have an odd, even, odd? Vertical shift. That one was pretty nice though, because the horizontal tangent went straight down to the intercept, so I knew that had to be an original and that had to be a derivative. And the horizontal tangent down to an intercept, so I knew F, then F prime, then F double prime. So the HTLs were really nice on that one. Maybe. Because increasing to increasing. Where's the one that I mentioned bouncing? A lot of you guys, you just had to approximate the slopes. Oh, it was Josh Jones. Oh, but you can't see it though. Struggle bus. Can I be a teacher for a second? I think I can. Can I do that and go to Josh Jones? No, that's not going to work. Struggle bus. Oh, I love this one. Can I check it? No. Oh, bummer. It's not letting me get it out of there. Oh, did I get yours wrong, Josh? Below then above, decreasing then increasing, approximate the slope. That guy is a -1. I think I had it right the first time and now it's mad at me because it doesn't let me even adjust it.
Oh, you have to click try again.
Don't act like you don't want to see it.
No, I want to see it, but I'm gonna laugh super hard when it's like not up to expectation.
Should I switch them?
But that is
It's gonna be very good.
Come on, guy, go purple.
They're like a big task of like 30 seconds. Like
So that's what.
because they put like 5 million people on it.
There's like there's been like a whole tube of these movies. Whole.
What are the other two?
Yeah, what's the other one?
-5, 1,
I like Wonder Woman.
2, 3, 4,
The Snyder
5.
Justice League is better than the
And the slider.
Oh yeah, that would be a much steeper one. So I did have to switch.
I was like, yeah.
But that's it.
Bummer. Should have
They hate the fans.
What they want.
They hate the fans want a good movie, they give them bad movie.
approximate slopes.
They want them to read books. Yeah, and then
Ah, I missed Hovans and Josh Jones. Good job, guys. All right, cool kids. You guys should be able to, I don't know if you can actually see what I was submitting as far as descriptions. The two I missed, I should have approximated the slopes on both, which was a bit of a bummer. But you guys also made some crazy hard functions, and so you did a great job on those. You guys can go ahead, and as soon as you have made at least attempts on all of them, you can mark as done this entire assignment, because I think most of you should have already done this one before. We did most of this one together, right? We did most of that one together. All right, cool kids. So we have 2 little pages of 4.1a notes to take, and then we're going to see how WebAssign went for you. That's the other window you guys should have open. So 4.1a, that whole idea of connecting f prime with f double prime with f triple prime. No, f with f prime with f double prime. Remember, there is like a whole Khan Academy section on that as far as going into more, not detail as in harder examples. You guys came up with crazy hard examples. But as far as this entire section of connecting f prime with f double prime with single f, etc., like you have some nice little practice problems. I mean, there were 2 sets. We might come back to that another time. There's also like a little quiz you can take as far as, okay, so the crazy hard ones were a little bit intense, but let's get a little more basic. Khan Academy can give you that practice, and remember that link is zoom right there. But let's get back into our goal for today, which is finishing up 4.1a. Double check me. You're in WebAssign. Is that deadline 11:59 tonight? Okay. Let's go ahead and finish this up then. There's a couple vocab things from last time that we didn't finish. One of them was this guy, which was, what do we call all the different possible functions that we get when we do a plus C? It's not a single, I think Rocco, you said this last time, didn't you? Like it's not a specific solution.
Right.
Yeah, right? It's more general. So this is what we could call a general. A general solution. A general antiderivative, but when we're answering any indefinite integral, aka an integral without bounds, that's what indefinite means. You'll see what bounds are in a future section. I think it's 4.3. I think it's 4.3. But we're just going to call them a family because it's basically all the different ones. So example, if I was to take something like, let's see, what was that one that we really, really liked? It was the parabola to a linear to a constant, right? So let's say I was to antiderive something like a 3x. My antiderivative would be, Josh Yang, use that rule that you said today. What would that antiderivative be?
For which one?
For the integral of 3x dx.
3x dx, that would be 3x squared divided by 2 plus c.
Good. Using that backwards of the power rule, right? Not the n comes down, subtract 1, but the n plus 1 and divide by n plus 1. But what would that look like? Well, it'd be 1.5x squared, so it's like x squared just a little bit steeper. But what if it's just at c? Okay, cool. Or what if it's at 1? Okay, cool. Or what if it's actually probably be a little bit out? Or if it's at 2? Or what if it's at -1? How many of these could I draw? Infinitely many, right guys? Because I don't know exactly which one it is. All I know is it's one of them. It's one of them with a vertical shift. So basically all the different possible solutions, that's what's called the family. So they're off by vertical shifts. And there is no way of knowing what the particular solution is unless what if I was to say something like given for up above the point 0,3. If the point 0,3 is on the parabola, the only parabola that would have the point 0,3 is the one that was shifted up 1, up 2, up 3. Then all of a sudden I would be able to say, oh hey, now I know the particular solution. You can only know the particular solution if given. And in physics, we would say something like an initial condition, and actually in calculus, we do too on the next page. At the very, very bottom is a really important concept, but don't worry, we're going to totally come back to it in a future section, so I'm just going to put this in parentheses. We're going to kind of have a few homework problems, or maybe like even sample problems, if we don't get to it today, maybe another day, that kind of show this to us, but we're totally coming back to this concept, so I'm not going to stress about it too much. There's something called the fundamental theorem of calculus that has us deal with that more. But for right now, what we're leading up to is, okay, you have a family, it's general, whatever, I don't know, plus C, and then all of a sudden, well, wait a minute, but I can find plus C. I can find a particular solution if we're given an initial condition. So we can solve for that constant of integration. Remember, that's a snazzy name for C. When given a particular point, we can have a particular solution. But wait a minute, did anybody see anything in homework where they weren't even given an integral sign? Did any of your problems in homework not even give you integral signs? Like, where's the integral in number 9? So let's talk about what this means. If it says solve the initial value problem, what you're being given right here is you're being given rate and an original point. What they want is find the original, let me say y equals f of x, that might be easier. That might be a little annoying. You're like, well, if they want f of x, then why didn't they put that as f prime of x? Well, you see, if we use section 3.7 of last chapter to split up the differential and get dy by itself, if I have my Leibniz notation, I can go ahead and get something that I can integrate. So technically, all of this would just be rewriting it, moving the dx to the other side, making 1 over 2x cubed 1 over 8x cubed, which is 1/8 x to the negative 3. But when you have it right there, it is primed and ready to go for an integral to be introduced. So if you don't have a problem that has an integral, but if it says, here's the derivative, and it either says solve the initial value problem or find the original function, or somehow it indicates go back. We go back by integration. Just get that dx to the other side. And now it's all primed and ready to, hey, nice, this is proper notation, let's go. And understood 1 could lead you to the integral of any 1. Any constant is that constant times the variable indicated. Look at your indicator. The variable indicated by the differential, that would be 1y. And over here, I'd have 1/8, and let's all try to do the power rule. Because the power rule would say plus 1 divided by plus 1 with my x to the negative 3. It'll take some time, but you'll get there. It'll take some time, but you'll get there. And you'll end up with negative 3 plus 1 is negative 2 times 8 is negative 16. X to the negative 2 is going to end up making it x squared in the denominator, but we're not done yet. Double check me though if you want. Negative 1/16 x to the negative 2. Remember, you can check every derivative. Sorry, every integral by taking a derivative. So ddx of 1/16 is the same thing as rewrite ddx of 1/16. Derivative of c is just 0, so that's fine. Bring down the negative 2, I get negative 1/8. X to the negative 3. Uh-oh, my negative's off. Oh, no, it's not. I had a negative. I just didn't write it. And then the negative comes down. That's thinking ahead. And then we have our positive. Oh, 2 times 2 times 2. So think back to just exponents in general. Cubed is 2x times 2x times 2x, and 2 times 2 times 2. Yeah. 2 cubed is 8. And then x cubed. I brought it up because I wanted a power rule. Is that okay? But once again, sorry, this entire page is saying what? Should I stay general, or am I supposed to be able to go particular? Because what was the extra piece they gave me, right? They gave me a point. So it's kind of like over here where I said, but what if? What if they gave you a point? Well, then all of a sudden they're choosing one for you. If they didn't give you a point, it's everything. It's general. It's plus C. But if they do give you a point, only one can work. So as soon as they give me a point, I'm like, oh, I'm not done yet. I need to go ahead and plug this in and say, okay, so y of 1 is equal to 0, and then plug in 1, and I get negative 1/16 times 1 squared is still just negative 1/16 plus C. I would need to add the 1/16 to the other side to get C, and then all of a sudden I know my final solution. So I plug in my point, I know my C, and all of a sudden I can go ahead and say that y is equal to negative 1/16. Nah, negative 1/16 x squared plus. Maybe there's some other ways of writing that with factoring and stuff, but we'll just leave it right there for now. So, general versus particular, we have some vocab. We have this whole family idea of everybody with the plus C. We have this initial value problem as a whole new category of, hey, you're integrating and plugging in to find a particular solution. So we have general, we have particular, we have initial value problem. I just didn't want to totally skip these pages because the vocab will come back. But after this, kids, like, I really do have like tons of practice that we could do. Oh my goodness, shush. But I'd rather just kind of see where you guys got stuck in WebAssign, and I think I have that up over here. So let me leave this on the screen for a couple more seconds as I pull up homework. You guys in WebAssign, let me know if you want me to go anywhere in particular for 4.1a, that guy we want to have done by the end of today. Yeah.
What do we call that? Y?
General solution, you know you're going to have a plus C at the end. General solution, you're going to have a plus C at the end. But also right away here at the beginning, we can look at like how they filled in. But when it looked super weird, what you were supposed to do to start was move that dx to the other side. That was step 1. So using what we saw in section 3.7, we're allowed to split these guys up, and you can't take an integral until you have your indicator as far as like, hey, I have my function with my indicator, now I can integrate. But when you're looking at the integral of dy, remember it's the integral of an understood 1 dy. That 5 can be thought of separately, like a constant multiple sort of deal. I'm going to do a power rule here, and then this guy, well, the integral of any constant is going to be just the variable being indicated, which in that case is just y. I could put like a plus c1 and have another plus c2, and then I could like move that over here to be a c3. I'm not going to worry about all those plus c's. I'm just going to say, hey, your c is going to subtract and add to be this guy's plus c in just a bit. But my power rule, like Josh was saying earlier when we did our first things first forevers, Works just the same here. So let's see what they're doing. They're saying to find the general solution of a derivative. So this is vocab. To find the general solution of a differential equation, they want you to go back. So Victor, kind of like your question. It's not super clear in solve the initial value problem, but I'm just saying, hey, that's vocab for go back. Same thing here. Find the solution of the differential equation. Here's the derivative. They want to know what came before, and coming before means an integral. So then they're just saying like, hey, set it up. But to set it up, we got the dy by itself. So all they want over here is just the 5x to the negative 6 dx. They're just having you get it ready to solve in like step 1. And then my guess is from there, you're actually doing like the solving part. But step 1 was just setting it up. Get that dx to the other side. Now you're allowed to take integrals. And once you're taking integrals, then you go ahead and use that power rule of, I wrote negative 6 plus 1, but we should know that's negative 5. And then 5 over negative 5 just ends up being a negative 1, or you could have just put the negative sign, and then they rewrote it just like, oh, hey, remember, that's an x to the 5th in the denominator. Now, they wrote it real awkward and real weird. I would have just written it negative 1 over x to the 5th plus c. I would have written it just like that. Because they're just reminding you, what did you just do? By taking the integral, you found the general solution. So you're just rewriting at that step. And then they say, check it. Well, check it, I take a derivative, and to take a derivative, I have my coefficient. I bring my negative 5 power down, and I subtract to be a negative 6 power, and it ends up being exactly what I need it to be. The derivative of the solution is the original. The solution of the original is the antiderivative. But some of those boxes might have been weird. Sarah, was there one of those that you didn't get to? Yeah, they were just rewriting it. Like start doing it, yeah. But does it make sense they just move that guy over? Yeah. Then they start anti-deriving. Any other places in homework that you guys want me to go look at real quick? We have a few more minutes. 4.1a. Give about 30 more seconds if someone wants to ask me something. On homework 4.1a. Remember, you're anti-deriving. You're going backwards. But to anti-derive, you might need to rewrite first. In order to get to these answers. These answers are not mental math. They're not done very quick. They take time. Some of them are just plugging in rules, but some of them take a bit more work. Ooh, especially like number 11. Oh, hey, how is the wording different in number 13? Anybody there? How is the wording different in number 13? Find the...
Particular.
Hey, what does particular solution sound like? Did they give you a... They give you a clue? You see it? No? Try it again. Particular solution. Remember, we're going to have a general plus C. I don't know. It's all of them. It's the whole family. Unless we're given a point. And if we're given a point, the terminology changes. They start saying stuff like an initial value problem or a particular solution. They've given me something else. So like Sarah just had us in number 3. All they gave me was a derivative. All I could go back to was a general. Where is he? Was a general antiderivative. I don't like how they wrote it there. I know why they did it, but I would have written it negative 1 over x to the 5th plus c. All I could have is a general. I have the whole family. Invite them all. But as soon as it's like, no, we want this one. You got to narrow down your search. You narrow down your search by getting the family, plugging in the point. Getting the family, I should say, plugging in the point, and knowing exactly what one you want. And so that's why in number 13, they're going to have you get way more specific. Today we were going to keep on going into motion, but for a few different reasons, I'm deciding not to do that. So instead, since you guys don't have any other questions, let's just practice with a few other basic ones, and then you guys will have until, let's see, our next class is on Wednesday. I'll go ahead and extend this one. It seems like quite a few of you have not gotten much done on it. I'll make it due like Wednesday at 8:30. That way you guys like come in right away. If you have questions, let's bust them out. And if you don't have questions, we get to move on. Is that cool? Okay, so it's supposed to be due 11:59 tonight. I'll go ahead and make it Wednesday, 8:30, as long as you do some examples with me right now. Deal? All right, so those of you just staring at your computers, let's get back in to do a few extra examples. I'll make them interesting. First of all, let's go ahead and skip this one for now. Let's go to this one. Hey guys, if they were to ask you to rewrite, I know you have some of these in your homework. How would you rewrite this guy first? Remind me you can do radicals. To the? Nope.
Ooh, 2 over 3.
Who is it? It's x squared. What's happening to that power? Oh, it's being cubed rooted. Careful. Careful. Can I give you a silly way of remembering that I don't think I'd ever seen before or used before? Hey guys, what would you call this radical? What would you call it?
1/4.
The what?
X to the 1/4.
Well, I was thinking the radical though. What root would you call it? It's not a squared root, it's not a cubed root, it's a it's a fourth root. Wouldn't you say fourth?
Oh.
Right? And what if I said like, hey, I want 1/4 of your donut? What am I talking about? Give me 4 of them? A fourth of it, right? Fourth root is a fourth power, right? Cubed root, a little bit hard. Cube power, like what's that? I don't know. I know. But 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, if all of them work this way, you just have to apply them to the square and to the cubed as well. Fourth root, fourth power, so cubed root is a 1/3 power, right? But this is x squared, so x to the 2/3. At this point, we would go ahead and then, I think in your homework it has a separate category for integrate. And for integrating, we would go ahead and use the power rule that hopefully all of us will be memorizing. Where we say +1, but why the heck am I adding 3 over 3? Because that's 1, right? Hold on. What is 2/3 plus 3/3?
5/3.
So I could write that again, and I could write it like this, which is okay, but I could also write it like, wait, why is she writing 3/5? What am I doing? I'm anticipating. I'm integrating. I'm thinking ahead. Remember the anticipation? X to the 5/3, dividing by 5, ooh. X to the 2/3 plus 3/3. I could do m plus 1 over m plus 1, but check it. Isn't that going to be multiplied by the reciprocal? X to the 5/3 times the 3/5. I've anticipated. I'm ready to be done. There's some of those in homework. Those get a little tricky. Make sure you know how to rewrite. What else can be in homework? What if you have something squared? I'm going to put a big old fat watch out over here. These are 2 watch out problems. Even if you're like, psh, I know how to integrate. Would you watch out? Would you know what to do? Chain rule. We haven't really done like a chain rule of integration. It's actually not called that. It's called U sub, and it's not for a while. So why is this example in the very first section if there's no chain rule? Oh, I could rewrite it. I could make it a product. Wait a minute. Is there a product rule for integration? No, we talked about that last time. There is no product rule for integration. But wait a minute. Just because there is no product rule doesn't mean that maybe I shouldn't think of foiling to rewrite it. I can't integrate with the product rule, but I can multiply the product. I end up with 4 plus 4y squared plus y to the 4th. Question. Can I do power rule to integrate that? products right now you guys cannot handle, but what you can do, there is no product rule for integration, so like take that off the table. If you go Googling product rule for integration, it's not there. There's another way we deal with it, and it's way more complicated. It needs chain rule. Backwards. Forwards? Anyway. Multiply. That's how to make it possible. Multiply. We can get things like, look at your indicator. It's not an X. What are my variables, guys?
Y.
So
Mhm.
why?
And I'm going to have 4/3 y cubed plus, I know I'm doing this one fast, but can you guys double check me and make sure I got them all right?
I also got that.
How could you check it?
It's derived.
Derive it. Derivative of 4y is 4. Derivative of, bring down the 3, it's gone. 4y squared. Bring down the 5, it's gone. Y to the 4. Woo! Takes time. Takes time.
I'm speedy.
A question.
Quickness.
What's so bad with this one?
Yeah. Quickness.
Look at your table. Look at your table. Cotangent squared. Oh, he's bound to be. No. Why am I having you review your forevers?
No. Oh.
Check out the Pythagoreans. The only legal way to integrate this guy is for us to realize it is cosecant squared minus 1, which is then possible to integrate because cotangent squared is not anywhere on that list. But guess who is? Cosecant squared is. And look, it's not that bad. You just had to use a little bit of tricks of. Bye, guys.
Wait, what property or what? How did you
Where is he? This guy. Remember there were 3 different variations. If I divide, let's see, cotangent squared to be cosine squared over sine squared. So divide everything by sine squared. That'd be 1 plus cotangent squared is cosecant squared. And then I subtract the 1. There were 3 different ones. I assume that you guys write them all. Maybe I should. I think I should. Maybe you did.
Maybe I should. Maybe I didn't.
Seniors, don't forget to tell Kelly I have a dingo block. I heard